Hey everyone, and welcome back to another AP Calculus video. Today we're going to talk about something called the Extreme Value Theorem, which essentially is an existence theorem that says that if we have a function that's continuous on a closed interval, in other words, when we look at the graph, we have closed endpoints that are closed dots. The Extreme Value Theorem promises us that there will be both a min and a max on that interval. So before we get into that and show you an illustration and a visual, let's talk about some vocabulary that we need to be familiar with. First of all, when I talk about maximum and minimum values, those are extreme values. That's what that word means, extreme values. It's talking about maxes and mins. And we can have two kinds of maxes and mins. We can have an absolute max and a min. That means it's the biggest or smallest value on the interval. There's nothing bigger, nothing smaller. It's absolute. We can also have these things called local mins and local maxes. And another word for local min or local max is this word relative. Now, this word relative, I kind of like it better because it means relative to the area directly surrounded. So in relationship to all the other points around it, kind of in a region, it's the biggest or the smallest point. It may not be the absolute biggest or smallest, but it is in that little area. Now, we also want to understand that when we say what is the max or the min, that question is asking for the y value. Okay, so the max and the min is the y value of the function. Now, if I say where is the max or the min, then I'm looking for the location. The location is always going to be the x value. So x tells us the location, y is the actual max or the min value. So now that we have that out of the way, let's take a look at an example here. And we're going to talk about how when we consider different intervals, we have different situations for the same function. So looking at x squared, here's the graph. It's a nice little parabola. It's really easy to see that x squared definitely has an absolute minimum value here. And so when I look at the graph, there's my minimum at 0, 0. And so the way that I'm going to write this is that y equals x squared with no interval, so it's the entire real number line that I'll be able to consider for the domain when no domain restrictions, that's the word I'm looking for. We have an absolute minimum of y equals 0, so remember the minimum value is the y value, at the location x equals 0. So that's how I'm going to write that. Now, I'm not always going to be asked for I'm not always going to be asked for the minimum or the maximum value. I will always be asked for the location. That will be the bare minimum of what I will be asked to find. Now, suppose that we change what we're looking at. We put a domain restriction on this. And so it might look something like this. Instead of looking at the entirety of y equals x squared, maybe I'll be looking at just a little piece. So maybe I'll be looking at just 0 to 2. And so my graph changes just a little bit and looks a little more like this little segment here. And if I trace the graph, you'll see that when I have a closed interval, that 0.24 is included. It's defined. And it's very clear to see that this is my maximum value. I also can see very clearly that 0, 0 is still my absolute minimum. So now by closing off that interval, I've added in an absolute maximum. And so here's how we're going to write this. We're going to say y equals x squared. But now we're going to say on the closed interval 0 to 2. So that means I have closed dots there. I now have an absolute max of y equals 4 at x equals 2. I also still have an absolute min of y equals 0 at x equals 0. So it changes a little bit when we change what we're looking at. So now let's take a look at another interval here. Now this one I do not include 0. So the way that we would see this is we'd say this is y equals x squared, but this time I'm going to open up that left side and I'm going to have an open interval on the left but keep it closed on the right. And so what it looks like is this. On the graph, 2, 4 is still included because that's my closed interval. So we can see clearly, yes, we still have a maximum value. We have an absolute max on the closed side. But then on the open side, check it out. My point is now undefined. And so there is no more minimum value. So we only have an absolute max. And I know it's absolute because it's the biggest on the interval. But now there's no min, okay? So one more scenario, what happens when we open both? Okay, so both sides. So now we're looking at this equation, y equals x squared on the completely open interval 0 to 2, but this time the endpoints are not included. So when I trace along with Desmos here, you can see I'm undefined now because that point is not included. And then down here, I'm still undefined. My point's not included. And so what that means is there is no more minimum and there is no more maximum on my interval. There is nowhere where I attain a maximum value because technically, because of that open dot, I can continue to go, you know, there's this idea that when you have a set fixed amount, like from 1 to 2, you can keep cutting it in half and you can go to 1.5, 1.75, and you'll always be able to go halfway to get to that end point of 2, but you'll never actually get there. And the reason you'll never get there is because it's an open dot, it's an open interval. So there is no max or min. We just don't have anywhere that we get, okay? So these are the scenarios, and the extreme value theorem really only addresses the red scenario here where we have a closed interval. And anytime we have a closed interval, we are going to be guaranteed to have both a max and a min. And sometimes it's the endpoints, but sometimes it's also going to be a point in the middle. But no matter what, you'll always have one of each if you are looking at a closed interval. So let's take a look at what this extreme value theorem says now. It says if f is continuous, so that's one criteria that needs to be met. We have to be continuous and connected on a closed interval. So you have to have these square brackets here. Then you are guaranteed f has both a max and a min on that interval. Sometimes it's the endpoints and sometimes it's an interior point. Now if a function has a local maximum at an interior point, then what's going to happen is if f prime exists, then that derivative will be 0. Now the key word is exists. If the derivative is there, in other words, as long as we are differentiable, you know, because you can have functions that have sharp corners, and that sharp corner can still be a max or a min. The trouble is, if there's a sharp corner, then the derivative doesn't exist. So we need to be able to think about that too. So if the derivative exists, it'll be 0. But if there's no derivative there, we need to consider that because it could very well be a max or a min. It could be a vertex of an absolute value or something like that. Or some similar. It could be a cusp where the two curves come together. So there's lots of scenarios. So all that to say this, critical points, which this is an extreme value, a max and a min, these are types of critical points. Critical points are just points where something interesting is happening, right? Usually it's a max or a min or something like that, but occasionally it's another type of critical point called a point of inflection. Now we're going to talk about those in another video, but essentially a point of inflection is where my graph changes from being concave up to concave down or vice versa. So we have a change in concavity. That's a point of inflection. Now those are special and we'll get to those another day, but for now what you need to understand is that critical values include extreme values. So to find extreme values, we need to find all of the possible critical values. And those critical values are where the derivative is 0, where the derivative is undefined, or if we're on a closed interval, the endpoints. So let's put this all into practice. So question 1 says, find the extreme values of this function on the closed interval. I'm going to have to check my endpoints because I have an interval. Find them and say where they occur. So we want the extreme values, so we want the y values, and we want the where, that's the x values. So we're going to need both. So here we go. Let's start by finding the endpoints. So we need endpoints. So what I'm going to do is I'm going to plug in f of -2. So that's going to be -2 to the 2/3 power. Now I don't have a calculator. If I had a calculator, I would graph the thing and find the values that way, but I don't have a calculator. And this is how your AP exam is going to be too. It's it's going to give you these types of problems without a calculator to use. So this is the process we use when we don't have a calculator that can just identify the max and the min for us. So here we go. I'm going to remember that I can rewrite this as the cube root of -2 squared. So remember, this is a power, and this bottom number is my root, if you are a little fuzzy on those rational exponents. I'm going to simplify this one more time, and I'm going to get the cube root of 4. So then I'm going to do the same thing with f of 3. That's going to be 3 to the 2/3 power. That's going to be the cube root of 3 squared, or the cube root of 9. Okay, so these are my y values. They could be mins and maxes, and actually they are mins and maxes. We need to figure out if they're absolute or just local or relative. So that's case 1, endpoints. Case 2, we need to find where f prime is equal to 0, and then we also need to find where f prime is undefined. So to do that, we need to find f prime. So let's go ahead and find our derivative. F prime of x is going to be 2/3, use that power rule, x to the -1/3. Now, I don't like negative exponents when I'm in this chapter. And the reason why I don't like negative exponents is because I'm looking for not only where is f prime equal to 0, but I'm going to look for where f prime is undefined. Let me show you what I need to do, and hopefully it'll make sense why I need to get rid of negative exponents. I need to simplify all negative exponents by taking them and dropping them down. F prime of x is 2/3, so there's my 2/3, x to the +1/3. Now, here's why I want to simplify, and here's why I like fraction and rational exponents, not exponents, rational expressions here in this unit. When I'm looking for where f prime is 0, essentially, if I have a fraction, I'm going to look for where the numerator of any sort of fraction expression I have is equal to 0. Now, since my numerator here is just 2, that's never going to be equal to 0. So there is nowhere where my derivative is 0. So I'm done with that step. But I still have to go on, and now I have to find where f prime is undefined. Now, where I'm undefined, that's where the denominator is equal to 0. So essentially, if I can get it into a fraction, if I have negative exponents, I like the fraction because the numerator tells me where the derivative is 0. The denominator tells me where the derivative is undefined. So where is the derivative, or where is this equal to 0? Well, x equals 0 is the spot where I'm going to have an undefined denominator. I'm going to have 0 in the denominator. So I figured out I have 3 critical values, 2 endpoints, and 1 spot in the middle where f prime is undefined. So now I need to figure out what my mins and maxes are. Now, where f prime is undefined, where x equals 0, I'm going to go ahead and I need to figure some things out, because just because I know that it's undefined, I know now that that could be a min or a max. The way that I tell what it is I have to consider the second piece of evidence that I need to provide to prove that a min or a max exists in a location. Not only do I need to show that the derivative is 0, or in this case undefined, but I also need to show that there's a sign change. Because remember, to have a maximum value on f of x, my slopes need to be going from positive to negative. I have to have a sign change with my first derivative. Same thing if I'm going from min to a max. I'll be going from negative to positive with my slopes. So I need to show that there's a sign change. So here is what I do. Show sign change. I'm going to label this f prime because I need to remember that I'm talking about a derivative here. I'm not talking about f of x. Later on we're going to have f double prime in there, so I want to label everything really clearly and organize my work. So f prime, this is my first derivative sign chart. And what I'm going to do is I'm going to pick values on either side of 0. And I'm going to see if my first derivative is positive or negative. So I'm going to do something like f of -1. When I do f of -1, or sorry, f prime of -1, that's going to be 2/3 times -1, and I'll zoom in a little bit here, to the 1/3 power. Well, 1 to the 1/3 power, or -1 to the 1/3 power is just -1. So here's what's going to happen. On this side, I'm going to get negative values. So I'm going to put a little minus sign up here above 0. Now I'm going to go to the other side here, and I'm also going to find something like f of 1. Well, when I do f of 1, I get a positive number. I don't even need to work it out. I don't care what the number is. I just care if I can tell is it positive or negative. Now, here's what we've just shown. We have shown that we have a sign change where my f prime is negative and then positive. And what that means is my original function looks like this. It's decreasing, which is why my first derivative is negative. It's decreasing, it hits 0, and then it's increasing. So this is kind of like my little graph of what f looks like. So now it's clear to see, oh, we're decreasing and then increasing. We must have some sort of minimum value at 0. Now, chances are pretty good that minimum value is like a cusp or something like that, or maybe it's a vertical tangent. You know, that's probably more than likely the case. I don't know. We'll see. It could be a cusp. It could be a vertical tangent. I don't know. But in any case, actually, it's not a vertical tangent because I see a sign change. So it's probably a cusp, now that I'm thinking a little bit closer on this. So we have a minimum at 0. Here's what we need to do next. My 3 critical values are the 2 endpoints. And now where x is 0, I need to find f of 0. So I'm going to go ahead and plug 0 into the original function. And I'm going to get 0. All right, now I'm going to do a little bit of thinking. Now, at negative 2, when I look at my sign chart, negative 2 is kind of over, let's see, we'll use a blue highlighter. Negative 2 is going to be kind of like over here somewhere, right? So essentially, my graph, where x is negative 2, it decreases from that point. It goes down, it hits 0, and then it comes back up. And where f is 3, that's going to be kind of over here. So essentially what we have is when we look at what's happening, my endpoint is a maximum on the left if I'm coming down from it, right? Because remember, we always move left to right. So if I start up here and I'm decreasing, that means that this negative 2 value, this is some sort of a max. And then I'm going to come down to 0, and this 0 is a min. So I have a max, a min, and then when I come back up on the right side, the rules are different. If I'm going up to the point, then the endpoint is a max. So my 2 endpoints are actually both maxes. Now, which one is absolute? Well, let's see if we can qualify this. My minimum must be an absolute minimum. Now, of these 2 values, which one is bigger? That's how you know which one's the absolute max. The cube root of 4 or the cube root of 9? Well, 9 is bigger than 4, so this must be my absolute max, and this must be some sort of local minimum. So when I summarize my findings, here's what I do. I'll say I'll have an absolute max, and I can just give the ordered pair at 3 cube root of 9. I have an absolute min at 0, 0, and I have a local max at negative 2 cube root of 4. Now, all this was done with no calculator. And if we look at the graph, we can kind of confirm our results. So here we are, evidence that everything I'm telling you is true. So here we go. We have an absolute minimum down here at 0, 0. And as we scroll our curve, we get up here. Sure enough, 3.208. That's that 3 to the 2/3 power. Same thing's going to happen over here. We've got our other maximum. And we can see that it's a maximum value because on the left I'm coming down. On the right it's a max because I'm going up to it. So it depends on what endpoint you're looking at. And then, of course, our absolute minimum, we can see it is, in fact, a cusp, and we know that the derivative doesn't exist there. So remember, mins can happen, mins and maxes can happen where the derivative is 0, somewhere in the middle. It can happen where the derivative is undefined, like a cusp or a sharp corner. It can also happen at an endpoint. So hopefully this is a good little illustration for you. So now that we've walked through one example, that always takes the longest, let's try a couple more examples here together. And some of these have some intense algebra, and it's important that you see this so you can be comfortable if you see it on your AP exam. So this question says find the extreme values of f of x and where they occur. So we're going to need to find some y values, but first we need to find some locations. Now I like this problem because there are no endpoints. So we're only concerned where is f prime equal to 0 and where is f prime undefined. These are going to be the two areas that I'm going to focus on. There we go. Well, let's write a little more clearly so we can all see what's happening. So essentially I just need to find the first derivative. So let's go ahead and do that. Now f of x is 1 over the square root. I need to change the square root to being a 1/2 power, and furthermore it's going to be a negative 1/2 power because that radical is in the denominator. So I'm going to rewrite this as f of x equals 4 minus x squared to the negative 1/2 power. Now I'm ready to find my derivative. So I'm going to use my power rule. F prime of x is going to be negative 1/2 4 minus x squared. When I take one away, it turns into negative 3/2. And then hopefully you recognize that this is a chain rule problem. So I need to do the derivative of that inside. I need to use that outside-inside rule. So chain rule is coming back to get me. So here we go. The derivative of 4 minus x squared is negative 2x. So chain rule. Here we go. F prime. I'm going to simplify. Negative times a negative is a positive. It's a positive 1, so I'm going to have x in the numerator. And then down in the bottom, I'm going to get rid of my negative exponent, and I'm going to rewrite it just as a positive exponent. I don't need to write it as a radical. This is just fine. So now I'm going to figure out what's going to be my zeros of my numerator. That's where f prime is 0. And what are the zeros of my denominator? That's where f prime is going to be undefined. So f prime will be 0 when the numerator x is 0. So where f prime equals 0, that's where x is 0. That was easy. Now the bottom, this one here, this 4 minus x squared, is a little bit more complicated. So where is this equal to 0? Well, it's where 4 minus x squared is going to be 0. Essentially, right? Because then when we raise 0 to the 3/2 power. So I don't even need to worry about the 3/2 power because I'm worried about what's going to make the interior 0. So here, x has two values, 2 and negative 2. So we actually have 3 critical values for this function that we need to explore. So now what we need to do is we need to find a sign chart. We need to see, is there a change in sign at these points? So when I make my sign chart, remember, I always start out and make my little number line, and I'm going to put the critical values, negative 2, 0, and 2, on my function, or on my number line. I'm going to label this f prime. Okay? And now here's where I want to make sure that as I'm plugging things into f prime, I don't ever want to write the numbers on the chart. I can kind of write them off to the side. So like I can do like f prime over here for negative 2, and I want to actually get away from plugging numbers in. What I want to do is I want to start getting myself in the habit of thinking, what is the sign going to be? So remember, f prime is x over 4 minus x squared to the 3/2 power. So here's what's going to happen. When I plug in negative 3, something like that, the numerator is going to be negative 3. So I'm going to have a negative on the top, right? So I'm going to make like a little fraction here, and I'm going to say, well, the numerator is going to be negative. Now I'm going to figure out, is the denominator also going to be negative, or is it going to be positive? So when I plug in a number like negative 3 or something like that, it's going to be squared, and it's going to be something like, 4 minus 9. Well, that's going to be negative 5. I'm going to cube negative 5. It's going to stay negative, but then I'm going to do the square root of it. And I'm actually going to get some imaginary numbers. So what's happening here is that on the way left side of negative 2, anytime you get anything imaginary, we're going to say that this function is undefined. The derivative doesn't even exist on this left side of negative 2. And in the same way, when I go over here to this other side here at positive 2, and I consider these values, I'm going to have a positive in the numerator, like positive 3. But you guys, when I plug in positive 3, the same result is going to occur in the denominator. I'm going to get like 4 minus 9 because of that x squared. And so I'm going to have imaginary values here. So it's undefined. So we've got some weirdness happening on the outsides. Let's now go into the other intervals and let's plug in something between 0 and negative 2. So let's look, we'll come back to those and see what's happening beyond 2 and negative 2. So here we go. When I plug in negative 1, I'm going to have a negative in the numerator because the negative 1 goes in for x. And in the denominator, I'm going to have something like 4 minus 1. Well, that's a positive value, so it's going to be positive. So all in all, negative divided by a positive is going to be a negative. Okay, so this area is going to be negative, which means my function's decreasing in that little interval. Now from 0 to 2, when I go to plug those numbers in, I'm plugging in positive values here. I'm plugging in numbers like positive 1. So when I plug in positive 1 for x, it's positive. In the denominator, it's also positive. So here, positive over a positive means overall, this little region is positive. So here's what's happening. When I think about my derivative, the derivative is undefined over here. So weirdness is happening. But I know that on this interval from negative 2 to 0, I'm decreasing. I get down to 0, and then I'm increasing again. Okay? So I know that this is what's happening with this particular function. Okay? So now let's talk about what's happening at 2 and negative 2. And to do that, I need to go back to my original function because 2 and negative 2 are critical values, and there is something happening there, but now we need to determine what the heck it is that's happening there so that we can make a statement about what kind of critical values those are. So now to do this, what I'm going to do is I'm going to find the y values at each of my critical points. So my 3 critical points were this. X equals negative 2, x equals 0, and x equals 2. So f of 0, well, that's easy to find. F of 0 is just 1 over the square root of 4 minus 0. That's the square root of 4. It's just going to be 1/2. So I'm plugging things back into the original function. F of negative 2 is going to be 1 over the square root of 4 minus negative 2 squared is, 1 over 0. Yikes. I have a 0 in my denominator, which must mean that I have a vertical asymptote. So critical values are more than just extreme values. They're also other things on my graph. It's somewhere where something interesting is happening. And in this case, I have a vertical asymptote. And if we plug in 2, we're going to find the same thing. We get 1 over the square root of 0, which implies there's some sort of a vertical asymptote there. So truthfully, we only really have one critical value here. We have a critical value, one extreme value here, and it's at the point 0, 1/2. And based on my sign chart, it must be a minimum because my function is decreasing and then increasing. So we're going to call this our absolute minimum because there's no other place where we have a critical point. And 2 and negative 2 are our vertical asymptotes. So let's take a look at the function and see what it actually looks like, and we'll kind of match what we have on our screen here to what the graph looks like so we can truly understand what it is that we are finding with our analytical algebraic approach. And so here we are at the graph. So here's my original function, and we can clearly see that yes, we have a minimum value here on the graph at 0, 1/2. So that was what we found analytically on our screen prior to this. And we can also see that, yep, we really have some vertical asymptotes here. So we're going to have undefined derivatives. We're going to have situations like that where maybe negative 2 and 2, if there's no function to find over there, just because they're a critical value doesn't make them an extreme value. So critical values, remember, are just places where interesting things are happening. They can be maxes and mins. They can be points of inflection. Or, as we just saw here, they can be vertical asymptotes or other interesting spots on our graph. Now to wrap us up, we're going to look at one last example here where we have a piecewise function, because these are just kind of a little bit different. And so to close us out, if we want to find the extreme values of a piecewise function, essentially the first thing we're going to do is we're going to find the derivative. Now to find the derivative of the piecewise function, you just take the derivative of each piece. So the first piece has a derivative of negative 4x. The second piece has a derivative of 1. And of course, we're going to keep the same x values. Now, we want to figure out where is the first derivative 0. Where is f prime of x going to equal 0? Well, the only place it's going to equal 0 is in this first piece, and that's when x is 0. So when x is 0, we're going to have some sort of critical value. The other thing we need to think about in a piecewise function is where the two pieces come together. Number one, is it continuous? And number two, is it possible that that could be another spot where we have a min or a max? So when I find my f of 1, and I don't know if this is the proper way to write it, but I will just kind of plug it in, and with the understanding that 1 is only included in the numerator. But here, f of 1, we want to see if it's continuous. So when I plug 1 into the numerator, I'm going to have 5 minus 2, that's 3, and then here. So we are continuous. Now we need to figure out if I'm differentiable. So at 1, f prime of 1 is going to be two different values. It's going to be negative 4 and 1. So what this means is it is not differentiable. So the first derivative doesn't exist here. It's differentiable. There we go, got to spell it right. So f prime is undefined. So this is another critical value point. And so we now have 2 points to consider. We've got 0 and 1 because of the way the graph is behaving. Now remember, we're undefined because the limit as x approaches 1 of f prime as we're approaching from the left does not equal x approaching 1 from the right. That's the technical definition of being not differentiable or having the limit or having the derivative undefined. So because we have this situation, now we're going to figure out what's going on. Well, when f prime of x is 0, when at 0, I'm going to make a little sign chart. So 0, and I'm going to figure out what's happening there. On the left-hand side, when I plug in negative values, so I'm only going to be concerned with 5 minus 2 times x squared. So when I plug in like negative 1, I get positive numbers here. I'm going to have positive values. So remember, I'm between, or I'm to the left of 0 here. So I'm positive, which means my function must be increasing. Now over here, I have to consider between 0 and 1. So between 0 and 1, when I plug in like 1/2 or something like that, and I evaluate it between 0 and 1, I need to think about what are the kind of values that I'm getting there. And I'm actually going to back up because I made a classic mistake of considering the original function when I should have been considering the derivative. So let's go ahead and label this like I should be doing. And here we're considering the derivative negative 4x. So again, when I plug in values to the left of 0, I'm going to have negative 4 times a negative number, and it's still going to be a positive value. But then on the right-hand side, when I plug in values like positive 1/2, any number between 0 and 1, I'm going to get a negative result when I plug it into this f prime function. So now this leads me to positive 1. Now I have to figure out what's happening at positive 1. So when I think about numbers beyond positive 1, I'm going to realize that here f prime is 1. So the derivative is a different value. Well, it's a positive slope, right? So no matter what happens here, I'm going to have a positive first derivative. So I do have a bit of a sign change, which tells me that I must have some sort of a sharp corner where the parabola comes together with a line. And then the line is increasing. So this tells me that my function really probably looks something like this. I'm increasing and then I'm decreasing until I get to 1, where then I start increasing again at some undefined value at 1. So this is what my piecewise function looks like. And if we look at the graph, we'll see just this. Now, let's label our points, and then we'll be done with this type of a problem here. So I'm increasing, so this must be a max. So I'm going to say I have some sort of max at x equals 0 of, and then f of 0 would be just 5. And then I'm going to have a min at x equals 1. And so now I need to look and see what it is. Oh, well, it's 3 of f of 1 equals 3. So there's my y value. So there's my min and my max. And those are local mins and maxes because we can tell from our graph that, you know, this will keep decreasing. There is no absolute min or max here, just a local min and max. So again, the key here is when you're finding these values, just to kind of sum it up, we're looking at 3 places. We're looking at endpoints where the derivative is 0, where the derivative is undefined. And then we always need to make a sign chart and see what's happening with that first derivative. Am I positive or negative, so I can tell if my original function is increasing or decreasing without looking at the graph. And then, of course, do not make the same mistake that I made. Don't let fatigue get the best of you. Always make your sign chart using that derivative, not the original function. That way you're going to tell if your original function is increasing or decreasing. So hopefully this has been helpful. This is one of the toughest topics that you're going to be asked to do during this first beginning part of AP Calculus. So my encouragement to you is to practice and realize that you're going to make a lot of mistakes. Be willing to work in pencil and do a lot of erasing. And you can see that even I, who have been doing this year after year after year, still made the rookie mistake of testing my sign chart with my original function. I did catch myself though. But you're going to make the same mistakes, and it's okay. You're learning. So mastery doesn't come right away, especially with tough things like this. If it was easy, everyone would do it. So keep at it, keep practicing. Don't let mistakes get you down. You're going to get it. It's a tough thing, but you can power through, and you can do this. You've got this.